Hello, welcome to my channel. My name is Loanch. In this video, we're going to try to determine the volume of a donut where the inner radius is A and then the outer radius is B. Good. Okay, so the shape or the diagram I have here, well, it's too perfect for a donut. A donut, due to the fact, is always more imperfect. But in fact, this is what I would call the modeled shape of a donut. That is to say, every donut who dreams of looking like this, but they don't. This shape here is called a torus. So by finding the volume of this torus, we're going to call that the approximate volume of our supposed donut. Well, I'm going to think about a cylinder. So let me put a cylinder down right here, just a sketch. Okay, good. Now if you fold this cylinder, you fold it, you think about having something like this. Though, of course, in the process of folding, you may need some infinitesimal partition, all right? But that's just the general idea anyway. And I'm going to also consider this towards the end of the video. Now, the cylinder will motivate us to use cylindrical coordinates. So I'm going to call cylindrical coordinates. It is a three-dimensional version of polar coordinates. So there we have x to be r cosine theta, y to be r sine theta, and then z as z. So z is responsible for the height. Okay, great. Now, the next thing we'd like to do is to determine where each of these parameters lie. Where r lies, where theta lies, and then where z lies. We look at the three of them because we want to find the volume. Okay, well, it is easier to think about theta because this right here goes round. That means theta has to go between 0 and 2 pi. So we say 0 is less than theta. Okay, it's less than 2 pi. Well, you may be worried about this equality with 2 pi as well, given that we have equality with 0. But it doesn't really matter because this is just going to be like a single point, which doesn't add anything to the volume. Okay, so how do we know where r lies? Well, I'm going to think about this thing here as, of course, what it is, a torus. Then if we look at it from above, we're going to see a flat figure, which is going to be an annulus. So we're going to have something like this, and then that. Okay. So we'd like to know what the radius is or where the radius lies. So you notice that B, okay, goes from this center to this point right here. That is the B from the diagram. So we have that to be B. And then A is the inner radius, which goes from here to any point on this extreme. So that means that from here to here is going to be B plus A. So we call that B plus A. That's the entire length. In other words, the radius of the larger circle is B plus A. So what's going to be the radius of this smaller circle? Well, since from here to here is B, and then this little part is A, it means that B minus A is going to be the radius of the smaller circle, B minus A. In other words, our radius, which takes the entire space here, this entire region, is going to go from B minus A to B plus A. So maybe I'll just put that down. So it's going to be from B minus A to B plus A. Okay, great. Now we are left to determine where Z lies. So let's think about it. So since Z is responsible for the height, we are going to cut across, maybe slice this torus, okay, along the radial axis. So we have something like this. So we're going to have, this is the Z axis, maybe this is the R axis. So we're going to have something like this. Good. So the inner radius is A, as we can see here. Then where does this circle lie? That is, where is the center of this circle? Well, since from here to here is B, it has to be B on the R axis, and then 0 on the Z axis. In other words, the center is B, 0. So we can form an equation of a circle with those parameters as R minus B squared plus since the Z coordinate is 0 for the center, we're going to have Z squared equals to the square of the radius. Okay. So from here, maybe we can think about Z as maybe Z squared will be A squared minus R minus B squared. Okay. So you notice that if we take the square root of both sides, we're going to have positive or negative version. And that tells us where Z lies. So we can say that Z lies between negative square root of A squared minus B squared, not minus B squared, A squared minus r minus b squared, and then the positive version of that, square root of a squared minus r minus b squared. Okay, so that's where z lies. Good. So maybe we can think about a solid. Okay, so I'm going to clean this off, and then I'm going to write down our solid. That is the torus. Okay, and then we're going to integrate over that to get the volume. So this is what the solid would look like. Okay, so let me show you what I mean. Okay, so we can generate our solid to be a set containing r theta z, such that this holds r lies between b minus a and b plus a. Theta lies between 0 and 2 pi, so 2 pi is included as well. Like I said, it's just going to be a point, or in general, a set of measure 0, which will not add anything to our volume. And then z lies on this interval. Good. Okay, so to find the volume of this torus, we're just going to find the triple integral over the solid E, okay, and then dv. Good. So we take the triple integral operator as a single operator, but we can rewrite this as an iterated integral, and that will give us the integral. Maybe let's start with theta. Theta goes from 0 to 2 pi. Then the integral as r goes from b minus a to b plus a, and then lastly the integral as z goes over this. So maybe let me just call this thing here z naught. Okay, so permit me to just do that. So I'm just going to call this z naught just for simplicity. That means we're going to go from negative z naught up to z naught. Good. And then we're going to have the dv, which is r dz dr d theta. Okay, from cylindrical coordinates. Okay, so we notice that, well, this integral doesn't depend, these other two integrals don't depend on theta in any way. That means we're going to have to evaluate the theta integral first, which will give us 2 pi, and then we'll multiply that by, well, this over here, which is the integral from b minus a to b plus a. And then notice this is just r, which is for the dr integral. So you notice this, that this is dz integrated from this to that, which will give us 2z naught. But well, since we call this z naught, I'm going to say 2, that is 2 times of this right here, which is square root of a squared minus r minus b squared. Good. And then we're going to put the dr right here. Okay, that's nice, because we evaluated this and we evaluated that. Okay. Well, the next thing I'd like to do is substitution. I'm going to make a substitution. I'm going to say let u be r minus b. Well, in that case, we're going to have the du to be dr. That's just a linear stuff. Okay, so making that substitution, we notice that the integral will become 2 pi times 2. Maybe let's call that 4 pi. Okay, then the integral, well, from b minus a to b plus a. But when r is b minus a, we notice that we're going to subtract 1b from that, which means we're going to be left with negative a. And then when r is b plus a, we're going to subtract a b from that, meaning we're going to be left with a positive a. Good. And then we're going to have r right here. But from this substitution, r is going to be u plus b. So we're going to call that u plus b. And then we multiply it with the square root of whatever we have there, which is a squared minus r minus b squared is going to be u squared from the substitution. So we call that u squared and then du. Good. Great. Okay. So what next? Well, I'm going to split the integral into the sum of two integrals because of this sum over here, which means we're going to have 4 pi times the integral from negative a to a of u times the square root of a squared minus u squared du. And then the other part with the b, which means we're going to have plus 4 pi b. Okay, then the integral from negative a to a of the square root of a squared minus u squared, then the du somewhere there. Okay, nice. Okay, so you notice that the first integral, well, you can make some substitution to that. But it is easy to see that we're having to integrate this function over a symmetric interval. Then what kind of function is that? Is it positive or, is it odd or even? Well, this is an even function, while this is an odd function. So we take the product of an even function with an odd function, you get an odd result. So integrating an odd function over a symmetric interval, you're going to get 0, which means the first integral breaks down to 0. Good. So we're going to add that with, well, the second integral, the integral from negative a to a of the square root function. Well, I can think about that as this. So I'm going to call that square root t, which means if you take the square of t, you're going to have a squared plus b plus minus u squared, rather. And we can easily rewrite that as u squared plus t squared equals to a squared. Good. So that is an equation of a circle with center at 0 and then the center at the origin and then radius of a. Well, we can easily get the area of the circle to be pi a squared. But you notice that here we only consider the positive square root, which means we're going to consider the upper part of the circle. In other words, it's going to be the semicircle above the x-axis. So from the formula of a semicircle, it means that we're going to have 4 pi b, which is outside. Then from the circle, we're going to have half of pi a squared, which is the area of a semicircle. Okay, so we're going to do those two easily. We're going to have this and this will cancel, leaving us with 2. Then we're going to have pi squared, then a squared b. Good. This right here is the volume of a torus with inner radius of a and then outer radius as b. Okay, but I said I was going to talk about cylinder really well. Okay, so if you want to evaluate this, maybe it's a different way. There are many ways of doing this. So the second method will be thinking about it as a cylinder, okay, that you can fold over. Good. And also the fact that volume can be determined by a cross-sectional area and then distance covered or height. Okay, so in this case, we're going to consider it as distance. Okay, so you may notice that I multiplied pi with pi, but I wrote only a single pi instead of pi squared. So that's a correction over there. Okay, great. Okay, and now we're going to think about a cylinder. So maybe let me draw a cylinder right here, and then down there. Good. Now you know that this cylinder has some height. So maybe let's call the height h, and then the radius of the top or the bottom, right? So the radius from here to here. Well, think about it. If you fold this cylinder over, okay, so that you have our torus, so something like this. Notice that this inner radius, this radius is going to be the same thing as the inner radius. So I'm just going to give it the same letter A. Okay, good. All right. That is to say, from here to here is our A. So maybe I'll just say from somewhere here to here, such that this right here is some cross-sectional circle. Again, notice that the height, okay, can be thought of as this as well. So this is also the height. That is going to turn out to be the centroid of this shape. So the centroid here, which describes a circle itself. So if you to find this centroid, you just have to find the circumference of a circle where the radius is from here to here. But we know that to be b from our initial data. So this is b. So the centroid there, as the length of that centroid, is going to be the circumference of a circle with radius as b, which is 2 pi b. Good. And then the cross-sectional area, since that's the distance, which is the height from the original cylinder, the cross-sectional area will just be pi r squared. Okay, but remember or recall that the inner radius there is a. Okay, in other words, to find the volume, we just have to find the cross-sectional area times the height. In this case, it's going to be the distance 2 pi b, which is going to give us pi a squared. So we say pi a squared times the height, which is times 2 pi b. Okay, great. So multiplying this out, we're going to have pi times pi. That will be pi squared. Then we have a squared, and then we have b, which is the exact same, imagine this pi squared, which is the exact same result that we had earlier. Okay, anyway, thanks for watching. Hope you enjoyed the video. Please don't forget to subscribe to my channel, share the video with your friends. I'll see you in the next video.